Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. Today we are going to talk about martingale and random walk. So in the previous lecture, we have been talking about Markov chain, right? Well, we know that xn plus 1, a future state, will be only conditional on the present state, right? It is not related with any x0 or x1, all these historical things. And intuitively, you are now starting to think that if we take the sum of all these states, right? Well, and what's the usage of that? That's basically the definition of random walk. And we are going to call that with Sn, with n larger than or equal to 1. So the term comes from the fact that we can think of Sn as a position at time n for a walker to make consecutive random steps x1, x2, all the way to xn, where xi can only take value 1 or -1 with probability p and 1 minus p respectively. And this is a simple random walk. And furthermore, if the probability is the classic 1/2, this Sn process is going to be called as symmetric random walk. And it is easy to show that the expectation of this sum of both x, Sn is going to be 0 because it has equal probability to be 1 and -1, right? And the variance is just n itself, okay? Which means the further this random walk lasts, the longer this random walk lasts, the variance is going to be larger. It is related with the time it has been accumulated. So symmetric random walk is a process that is mostly tested in quantitative interviews. They are often revolve about finding first n for which Sn reaches the definite threshold alpha, or the probability that Sn reaches alpha for any given value of n. And this is called stopping rule, which we are going to talk about later. But first, let's talk about martingale. In Chinese, we call it yang. Okay, we call it yang. Martingale. So a martingale, a lovely name, right? Is a stochastic process with the property that the expectation should not be infinity and conditional on all the previous state. This Zn plus 1 should be the same with Zn, okay? And the property of a martingale should be extended to all the way Z with n plus larger than n, and this should also be Zn, which means that the conditional expected value of future Zn is just the current value Zn. And we can all the way, using this property, we can all the way bring expected Zn to what? To expected Z0, right? The initial stage. And basically a symmetric random walk is just a martingale. Because from the definition, we have Sn plus 1 is going to be the same as Sn, and it is going to be all the way to be Sn minus 1 all the way to expected of S0, which is S0. And similarly, since by mathematical calculation, we can have the formula here, and we can find Sn squared minus n is also a martingale. And please remember this one, because this is, let's call it formula 1, right? Expected Zn equal to the original Zn. And this is what expected Zn squared minus n is also equal to expect Zn squared minus n. So if this is 1, this is 2, combine these two together, we can solve some values out. So we will frequently using these two equations in the questions we are going to talk about today, okay? So now let's talk about the stopping rule. Basically, the stopping rule is just the concept I just discussed here. So it means that for an experiment with a set of IID random variables x1, x2, there should be a stopping rule that once the xi reaches some level or touches some threshold, then this whole process is going to stop. And basically, whether to stop at n depends only on xy all the way to xn. It is not related with any future states, basically like xn plus 1, xn plus 2. And now we have the Watts quality. So n is the stopping room for I, the random variables, and Sn is the sum of these random variables. We can have the expected value of this random walk Sn is going to be the multiplication of the expected value of each single x. We multiply by the expected value of this stop rule n. And this is an important that relatively little known theorem. The proof is listed here. I'm not going to type in all that, but what I want you to remember is that a martingale stop at the stopping time is also a martingale. So how to understand this word, this sentence? Basically, let's use this Sn squared minus n as an example. So if we replace this n here as a stopping room, then since Sn squared minus n is a martingale, if we replace this n with this larger n, it is going to be still a martingale, although this n is a what? Is a random variable, okay? N is a random variable. It is not constant. It also has expected value and things like that. So you can think it as a function, as an independent function that is related with this process, okay? So now let's try to solve some questions so that you can better understand those concepts. The first question is that the drunk man. So a drunk man is at the 17th meter of a 100-meter long bridge. He has a 50 probability of staggering forward or backward 1 minute each step. And what is the probability that he will make it to the end of the bridge before the beginning? And what is the expected number of steps he takes to reach either the beginning or the end of the bridge? So we can see it is currently at the 17th place, right? So let's write, and it has a 1/2 probability of stacking forward or backward. So what we are going to ask is that the probability, let's call it probability alpha, okay, is that bridge to 100 meter. And we can know that probability beta equal to reach to 0 is going to be what? 1 minus P alpha, right? And we know this is just a symmetric simple random walk, which is martingale. So we have what? The expected value of Sn, this n is a stopping rule, which is either, in this case, because we start at 17, so the stopping rule is going to be 83 or what? Or -7, right? And then expected Sn is going to be probability alpha multiplied by 83 minus 1 minus probability alpha multiplied by 17, because this is a -17. So how can we get this formula? We are using the equation that the Watts equation, that ESN is going to be EX and EN. Okay. And we know this is going to be the same as this 0, which is just 0. And on the other hand, oh, not this one. It is just a simple multiplication of this Sn, because at the stopping time, it can either have probability alpha to have 83 or to have the 1 minus probability alpha to be -17. This cumulative value of Sn basically is the length. Okay, and for the second equation, remember we are going to use both the equations. So Sn squared minus n is going to be what? So this part, it is the same. It is just expected value of probability alpha multiplied by 83 squared, because Sn is going to be 83 at that time, and plus 1 minus probability alpha, because negative 17 squared is going to be a positive value. So 17 squared. And minus En. This is going to be S0 squared equal to 0. And by solving these two equations, we can have probability alpha equal to 0.17, and expected N is going to be 1441. So you can see the final result is just what? It's just, let's write this as alpha and this is beta. So this is just alpha minus beta and divided by what? Divided by beta, right? So we can try to generalize the case. So let's write it here. If we have a symmetric random walk starting from 0, remember we showed starting from 0, okay? And we are going to stop at either alpha, which is a positive value. Let's use a simple denotation, or negative beta smaller than 0. And then probability stop at alpha is going to be beta over alpha plus beta. And the probability stop at beta is just what? Is alpha plus beta. And the stopping time is just alpha multiplied by beta. Okay, this is the general formula. And now let's come to the next question. So this question we have been talking about that in the previous chapter, probability theory, right? At that moment, we are trying to solve this question using the symmetric principle and the replaceable principle I introduced to you. But this time using Martingale, it's going to be super easy to solve this question out. Because for ESN, it is going to be expected X multiplied by expected N. Okay, so go back to the previous question. Why we didn't use this formula in this question? Well, the answer is easy, because expected value of X here is just is 0, because it is 1/2 multiplied by 1 plus 1/2 multiplied by -1. Okay, so it's useless to use that. But it's not the same in this question. We just need to apply this formula, and we can have the expected value of X, which means each time we toss the dice, we can have 1, 2, 3, 4, 5, 6, all with probability 1/6, right? So the expected return for each toss is just 7/2. And what's the expected number of N? So for the stopping rule, if I get 1, 2, 3, the game stop. Otherwise, I continue. So I have 1/2 probability to stop plus what? 1/2 probability to continue, right? So it is just a geometric distribution. With 1/2 probability. So the expected N is just 1. It's just 1 over the probability, which is 2. So we just use 7/2 multiplied by 2, which is 7. The expected payoff is just 7. Okay, get that? Quite simple using the Martingale properties, right? And now let's go to the third question, the ticket line. So for this question, we are going to introduce one more important principle. I call it midpoint, or we can call it reflection principle. So let's first read the question. At the theater ticket office, 2N people are waiting to buy tickets, and N of them have only $5 bills, and the other N people have only $10 bills. So the ticket seller has no change to start with. So if each person buys one $5 ticket, what's the probability that all people will be able to buy their tickets without having to change positions? So we can just try to first simplify this question. So of course, we want all the people that have $5 to pay the bill first, right? Then for those have only $10 bills, they can have their changes. So we can put +1 to people with 5 and -1 for each people with 10. And we combine this as x. And now since there are n people have 5 and n people have 10, it becomes what? A symmetric simple random walk, right? And for these 2n steps, we need to choose n step as +1. So how many ways to choose that? We're going to choose 2n from n, right? After consuming all these 2n people. So they are in total 2n and n factorial and factorial combination, possible passes. And we want this xn to be larger than or equal to 0 for any 0 from a from 2n. So during this whole process, okay? So, and how can we make sure that happens? The thing is that we just need to exclude the probability that this xn is going to reach smaller than 0. So how could that happen? So let's denote this as xn, okay? Xn, and it is going to start from 0. If the first people has $5, then we go to 1. If the second people also have $5, we go to 2. But eventually, because they are going to cancel out, there are n people have 5 and n people have 10. So at 2n, it is going to reduce to 0, right? So now we want it to be always above the line of 0, but now we want to consider the case when it comes to smaller than 0. What is the case? It is when it reaches what? -1, right? And once it reaches -1, it can either go back to 0 or go to -2. And because these two are all reflectable, if we have one path go back to 0, then we have one corresponding path goes to -2. And this is called the reflection principle. So to find all the paths that is going to bring us back to this xn here, we just need to calculate all the cases reaches -2. And we can find all the places rebounds back to the places above to 0. Why is that? Because once it reaches negative, it is going to stop, right? We do not need to count that path. So we do not need to consider a situation where it reaches -4 or things like that. We just want to find the reflection of all the things from -1 and goes back, okay? And then how many combinations to have to reach -2? To get -2, we need to have n-1 people with 5 and n+1 people with 10, right? So we need to choose n-1 out of 2n to have such number of passes, which is this number. And then we just need to use this part to minus this part, which is going to give us 1 over n+1 to n over n. And we divide it by 2n over n. We can have the probability able to buy their tickets without having to change position, which is just 1 over n+1. Okay, so I think the most important case is that you should use the reflection. So why should we only consider the rebounded case? It is because that for -2, it means the first set or the people whose sequence will bring us to the wrong situation comes up. Okay, so now let's come to the last question. This question I think is super classic. Assume you have a fair coin. What's the expected number of coin tosses to get n hats in a row? So I think the most simple case, the first solution is by induction. We just need to give it a try, right? So expect value to have one case to have one hat in a row. To get n hat in a row, let's define at fn, okay? Let's define this as the function fn. We know this is 2, right? Quite simple. And how about to get 2? Then by calculation, you can easily get this is 6. And you can also get to have 3 in a row is what? Is 14. How can we solve this out? We can just using, let's denote this as x, using this as an example. So x is going to be what? Is going to be EF. So we can, because we can have EF1 multiplied by 1/2 plus one plus 1/2 x, right? We can have this thing as equal to So we can just do using the replaceable method, because this x is going to be 1 plus 1/2 to be EF. So we should first start from EF1, right? And then there are 1/2 probability to have 1 and plus 1/2 probability to go all the way back. And we can know that x is going to be 2 EF1 plus 2, which is just 6. Okay. So, sorry, this should be 1 here. This should be 1 here. So because from F1, at least we should toss 1 times. And within, and then after that, we have 1/2 probability to get there. So we need 0 step, and we have 1/2 probability to go back to the original states, okay? And similarly, you can have EF3 equal to 14. So by induction, we can easily find EFN is going to be 2n plus 1 minus 2. Okay, so this is the induction method. I think basically by guessing, you can get the correct answer. But meanwhile, we can also using the formula place I just introduced, we can find EFN plus 1 is going to be EFN plus 1/2 multiplied by 1 plus 1/2 EFN plus 1, right? Oh, sorry, this should be 1. There should not be no 1/2, okay? But I want you talk about the general case. So the general Martingale approach is trying to explain this question by setting a game. So imagine a gambler has $1 to bet on a sequence of n hats in a fair game with the following rule. So we are placed upon n consecutive games. For example, we want to have n hats, And each time the gambler bets all his money unless he goes bankruptcy, okay? For example, if H appears at the first game, he will bet 2, he will have to because each time the return is going to be doubled. And he will put all his money back to the second game, and he can stop the game either when he loses the game or when he wins n game in a row, in case he collected 2n. And now, instead of one gambler, before each toss, a new gambler is going to join the game and bet on the same sequence of n hats with a bankroll of $1 as well. And after the ice game, there will be in total I gamblers, and the total money they have placed, will have the will be the same as the total bankroll, which is $I as well. And then we can denote this xi as the amount of money that all the participating gamblers have after the ice game. And then this xi minus I is also a martingale, okay? Because expected value of xi minus I is going to be x0 minus 0, which is just 0. And now let's add in a stopping rule where, you know, the whole game will stop if one of the gamblers become the first to get n hats in a row. And then what can we have? We know that xi, the total money put into these places, is just 2n plus 2n minus 1 plus all the way to 2, 1, which is just 2n plus 1 minus 2. Okay, so how can we get that? It is by the sequence at 1 minus q. This is 1 minus q to the n. And we have, this is, we multiply by 2 here. And we have q equal to 2, okay? And then once someone meets our equation, we can calculate the expected steps it is going to take. For example, if we want 3, if we want 3h, then we know what? Then we know xi is just going to be 2, 3 plus 1 minus 2, which is just 14. Okay, but the most powerful thing about this and about this dice sequence is that we can apply this to any sequence. For example, if we want a sequence HH, TT, HH, then what should we do? If someone wins this sequence in this game, then it must be what? If this is ice people, then if ice people is the last people attend this game, then I minus n plus 1 people is going to be the winner, okay? Which is going to be win 2 to the power of 6, right? Because it's a sequence of 6. But meanwhile, what is going to happen? The I minus 4 people, this is I minus 5, right? How about the I minus 4? The I minus 4 people is going to have H, T, T, H, right? So he is going to lose in the second toss T. So, and the TTH and TH, the I minus 3 and I minus 2 player is going to have 0, 0. And this is going to be 2, 2 because he loses in the second toss. And how about the last people? The last people has H, which wins 1 toss, which is 2. So we know this expected value of xi minus I is going to be 2, 6 plus 2, 2 plus 2, 1, which is equal to 0. Then we have what? We have EI and we minus EI, okay? We have EI equal to 17, which is sum of this part. So we can have the expected time to get this value. So this is actually a quite interesting way to solve all these kind of questions. We just need to find out any sequence we want, no matter like HTT, HH, and then go all the way back to the last one and to see for each of them how many dollars can they get. And then we can have this result. Okay, so basically that's all for today's class lecture. And next time we are going to talk about dynamic programming. So see you next time. Thank you for watching. And 不要忘了一键3连。